You're convinced now these aren't the same, right? They don't superimpose, right? So these are mirror images that aren't superimposable, therefore they're enantiomers. That is easy to see now, I hope, with molecular models, 3D modeling kit, or on the computer with Spartan, maybe dash wedge notation with drawing. Let's say we go in the lab. We're not going to be holding these anymore. We'll be having two vials in our hand. Let's suppose we have one of each enantiomer. We go in the lab. I say, oops, I forgot to label them RNS. I don't remember which one's which. Is there a way to determine that? Is there a way to determine the difference between them? Well, think about what an enantiomer is. They're non-superimposable mirror images. So they're kind of like the shape of one is the inverse shape of the other. So their intermolecular forces that rely on dipoles and electrostatic potential maps will actually be mapped identically, just the opposite direction. So that just means that they have the same physical properties, right? Because if their polarity ends up being the same, then they'd have the same boiling point, melting point, etc. So that's a problem. That makes it a challenge. Enantiomers have identical physical properties. And we're going to put a caveat to that in an achiral environment, which is most lab environments that we work in. You know, port in a beaker, port in another beaker. There's no way to measure the difference because the melting point will be the same, the boiling point will be the same. If we took a TLC, that would be the same, RF. But you might remember that they can smell different, but that's not a measure we always encourage using in the lab. It's often recorded in observations, but it's not always even safe to do that. So what could we do other than smell? And why does smell work? That's because our bodies are not in a chiral environment. They are chiral. Biological systems are chiral. So in a chiral environment, yes, we will be able to tell the difference. We will be able to even purify a set of enantiomers. And so there are methods to do that, like column chromatography that has a chiral column. To tell the difference between them, luckily, chiral molecules also happen to have this feature. They are optically active. And what that means is they interact with light, and enantiomers interact in equal and opposite ways. So equal and opposite. They'll have a value, a specific rotation value that is equal and opposite. So equal magnitude, opposite sign. So magnitude, I'll write that there. Opposite sign. Now diastereomers also, because they're chiral, will interact with that environment. As long as they are chiral, they will also be optically active, but they also are not superimposable and they're not mirror images. So they're not exact inverse copies of each other. So that means their physical properties are going to be different, right? So they will not have the same melting and boiling point. So they're easier to separate and analyze in the lab. Because what does separation rely on? Targeting differences in physical properties. We see two compounds and we see totally different boiling points. We say, aha, we're going to use boiling point to separate them, distillation. We see totally different polarities. We're going to use that. We're going to use column chromatography to separate them, tested by TLC. So getting back to optical activity. So I said chiral molecules are optically active. So optically active is synonymous with saying it's a chiral molecule. If you say something is optically inactive, it does not interact with light, then it's an achiral molecule. You don't really see it with just everyday white light. It's specifically plane polarized light. So what happens is the white light, it's polarized in all directions. You pass it through some sort of filter or like a Polaroid sort of lens, or this is a naturally occurring one called the Iceland spar crystal. That's a natural form of calcium carbonate that interacts with light in interesting ways. But what happens is the many planes enter and it orients them into one vibrational plane. So now it's plane polarized. Once you have a way to, that's the way the instruments work that measure optical activity. So once you have the light polarized, you're ready to put your sample in, and it'll interact with plane polarized light differently. if it is chiral. It'll rotate one way or the other way. If it's achiral, nothing happens. It doesn't change. Okay, so let's go through the outcomes. So let's start with our plain polarized light. Polarized, H nu for light. Enters your sample. So this could be a vial or a special sample holder that is used by the instrument, and it's got a length to it, right? And that's actually measured in decimeters for the calculation that we'll do. So if the light passes through completely undisturbed, in other words, it's plain polarized in that orientation and it does not rotate at all by any measure, that could mean one of two things. That could mean our molecule is achiral, or it can mean we have equal quantities of both enantiomers that are canceling out the effect of the rotation that could happen. So we'd say it's ororacemic, which is a 50-50 mixture of both enantiomers. So in other words, if it's enantiomerically pure, one enantiomer will rotate the light a certain number of degrees, depending on what that is. So I'll just kind of arbitrarily start there. So if this was our starting point, right? So this is our starting point. It rotated so many degrees, all right? And furthermore, so that's a magnitude, it went clockwise. When it's clockwise, we say it's dextro-rotatory, so right-handed rotation. Dextro-rotatory. So it gets the sign plus. This does not mean, just because it's a right-handed rotation, does not mean it corresponds to the R enantiomer. It could also be the S enantiomer. This is a measured value, not a man-made Conning-Gold-Prelog way of naming. So it could be S, also rotate to plus. It could be S, also rotate minus. It just depends from sample to sample. But then the good part about that is that we will know it's not the same as the other sample, the other enantiomer, which compared to the same point of reference starting point would rotate equally the other way, counterclockwise. So counterclockwise equals levorotatory, and that gets a minus in front of it. Okay, so to get the actual specific rotation value, that's called alpha, we get the degrees of rotation, so measured from here. So if this starts at 0, you can measure the degrees that it rotated. The length of the cell, it will vary with that. So just to be consistent, to account for that, we include that in the calculation. So the sample length that it has to travel through. And it also will vary with concentration. So much more concentrated will be different than very dilute. So the concentration is factored in. So that way you can get a consistent number across all samples. Okay, so when we talk about specific rotation, how can we interpret some of those numbers? So a racemic mixture, which is sometimes also called a racemate, means that we have a 50-50 mixture of enantiomers. 50% R, 50% S, or 50% RR, 50% SS. That means that they will have equal and opposite optical activity, opposite, resulting in a net value, if it's racemic, of 0. So 0 is the specific rotation. The same thing happens if we have chiral, like if we just put water in there, we see 0 rotation. So you have to keep in mind that if you get 0 rotation, it either means you have something that's totally achiral or two equal amounts of chiral things that cancel each other out. But if you have something that's actually chiral, it will change the orientation of that light, right? So how do we get the polarized light? Well, that Iceland spar crystal is not necessarily the only thing that could do that. Another really common filter of light comes in 3D glasses.
You'll love this game, it's so insania!
Okay, so here is a pair of glasses
you guess where they're from? If you guessed Toy Story Midway Mania, you were correct. Thank you, Disney, for the educational donation. I need 2 for this experiment, though. Now, if you've ridden that ride, you know that it's required for 3-dimensional viewing. So these are 3D glasses. Is there any reason, and what I have them on is a backlit light box. Is there any reason, so you can kind of see through them, right? Is there any reason to believe that one eye is different from the other? So the left eye, from what we could see right now, looks the same as the right eye, right? So if you like stack these up, like sometimes when they come back, you still see through them, right? What's interesting is if you ever get to go on that ride, or next time you go on a 3D sort of attraction, maybe borrow your friends or your neighbors' glasses and try this. Whoa, they actually block each other's light out. If you superimpose the right and the left eye, they actually don't let light through. So notice that? Oh, it's black, light's not coming through. But suddenly it comes through again. You can get the same effect by taking one eye and orienting it. So notice how it's transparent here and it's orthogonal, completely blocks out light. So that gives you a little insight on how these filters that are inside of the 3D glasses work. The left eye clearly has a filter or a polarizer that's orthogonal to the right eye. So it's taking light that's not polarized and polarizing it. And one thing we know about polarized light is that plain polarized light will travel through, just like any other light, will travel through a medium undisturbed if it's an achiral. But since chiral molecules have a kind of a twist to it, it will also twist the rotation required to get that same block out. So let's remember 0 degrees, we can see through, right? 90 degrees, we can't. And we've proven that these are essentially must be 90 degrees to each other, right? So now I'm going to take some water. We know water is not chiral, right? So I'm going to put that on the left eye. So there should be no difference looking through it. There might be a little bit of a dimming, but that's negligible, right? If you look to the left and right eye, they look the same. It still blocks, still treats the right eye as orthogonal. Now for the other eye, I'm going to go ahead and put something that I know is a chiral solution. Corn syrup contains a highly concentrated solution of carbohydrate sugars, which have a lot of chiral centers, mostly dextrose. So let's take a look. So it's very viscous. So you can see it might look transparent and colorless like water, but it's definitely not if you were to touch it. And so I just get that from the grocery store. So good old corn syrup bottle here. Now, this is something you could do at home if you have access to 3D glasses. So now they look the same, right? But we haven't tried to overlay a filter going in any opposing direction. So let's do that same thing again. We should be able to see through. Once again, remember, water alone, no change, right? Doesn't matter which eye, because it's your eye, and your eyes are mostly water, so it works. It remains undisturbed. But when we put corn syrup in, look at that. That's definitely tinted now. It's blocking some light out. It's not perfectly making it orthogonal, but it's rotating the polarized light. So what do we have to do to make that blocked out? Let's try rotating this. Notice that it gets darker. Oh, look at that. It's finally darker there. So depending on the sample and the thickness, I intentionally made those two liquids the same height because it does depend on how the thickness of the sample, but depending on the thickness of the sample, the distance the light has to travel, as well as the properties, the inherent chirality of the sample itself, we will have a different rotation required. And that's something we can measure more quantitatively. This is just a demonstration of the concept. So I don't have anything here with me to measure degrees because we have a better instrument for that. So notice that I could also go the other way to get it to finally block out. All right. And then once again, the orthogonal trick If it's black here, it should be completely clear and colorless here, and it's not. So kind of a cool effect, right? So you can see how it's clearly altered the angle required to let light in undisturbed and to block light out undisturbed. So it's a new angle. So that angle goes into the equation as well. And so we could get a degree sign at the end of the day to give us our what's called the specific rotation assigned to each sample. So each sample would have a different degree of rotation for this in particular.
So as mentioned, we can have a value of 0 when it's either achiral or 50-50. Okay, so in other words, for racemic mixture, alpha equals 0. For an achiral mixture, alpha equals 0. But let's say we have some numbers to work with. If an R enantiomer has an alpha, which equals -19 degrees, then alpha for the S enantiomer must be equal magnitude, opposite sign, plus 19. Actually, that's what the space was for down here. So it can be a little bit difficult to know that R means it's like assigned clockwise by the naming system, but that's like saying I named this group of people, you know, according to this name, and they can't have this property, which obviously that makes no sense. So this property of the molecule is irrespective of how we chose to name it. Okay. So in other words, R and S can have either sign. It doesn't correlate with their optical activity. But we do know that once we find something that's R versus S, they will have the equal and opposite magnitude. So if I measured this one and I said, hey, I found out this is -40, under the same conditions, this one would be +40, right? Okay, so one-to-one mixture of enantiomers, I used that word before. While that's called a racemate, what do we describe something that's not a one-to-one mixture? So we've talked about having all one enantiomer, so all of R, all of S, or 50-50 R and S, but that's not always the case. What if we have an unequal mixture? When we are talking about an unequal mixture, we want to know more information. Unequal which way? Do we have more R? Do we have more S? Are they still pretty close? So we use the term enantiomeric excess, which involves some easy calculations. I mean, it boils down to the percent R minus the percent S, absolute value, so it doesn't matter which one you're subtracting from which, where, remember that the total sum would add up to 100. Remember, the percent R plus percent S must equal 100 because those are your only two components. So you could work out what they could be. But it's also measured in the lab. So you can take your measured alpha. So you went in the lab and you measured it, but you know from literature values that the pure alpha is a different number. And you can get the EE from there by dividing those two and multiplying by 100. So here's a couple scenarios. Examples, I think, clear that up more than anything. If a sample is 90% R and 10% S, we can't call it racemic. We can't call it pure set of enantiomers. We'd have to describe it as a mixture with an EE of 90 minus 10, 80. 80% EE. If someone says, hey, if you say, what's the EE on that? That's actually a really common bragging right for synthetic literature papers to see how close they can get, because a lot of times they're trying to make only one enantiomer, but they might still make a little bit of the other. So they want to see how close they can get to purely only one enantiomer. So if they say, what's the EE on that? If we say, oh, it has 100, what does that mean? Remember, R plus S has to add up to 100. So that means there's only one of them. So there's only one R or one S. It only contains one enantiomer because the other one has to be 0. But if a sample has 0, then it contains, how do we get 0? EE. So R minus S, where R plus S has to equal 100. Well, then that would be what happens when you have a racemic mixture. That's how you describe the EE of a racemic mixture, 50-50, right? Because 50 minus 50, 50 plus 50 adds up to 100, so that pans out. But if you plug those two numbers in, 50 minus 50 is 0 for EE. So it contains both enantiomers, or 50%. Ready to level up that? Let's say we're in the lab. We find a bottle of dextroamphetamine. This is what actually is found in Adderall. You measure the specific rotation and determine that it is plus 20 degrees. So if it's labeled as dextroamphetamine, that's actually the right-handed one, the clockwise, that means that it has the plus, right? So it's labeled as S plus beta phenylisopropylamine, which is also known as dextroamphetamine, found in Adderall. So you're trying to decide how pure is this really? Because it's labeled as S, and maybe it's been sitting there for 30 years. You want to see how pure it is. Maybe the sample says it's impure. So let's find the EE. So you measure it and you say it's 20, but the pure sample is actually supposed to be 40, so it's off. That means it's not totally pure, right? So let's get its EE from that. So remember that the EE equals measured, so that's from the lab, alpha over pure alpha times 100. So that means measured was 20 and pure, the plus, was 40. That equals 0.5 times 100 equals 50%. So the EE is 50%. That does not mean we have a 50-50 mixture. What two things that add up to 100 when subtracted equal 50? Right? So remember, because this also equals, sorry, I lost it. Scroll back down there. So it also equals %R minus %S. But we know that R plus S makes 100 because that's how you get the total amount of those are the only two components present. So what two things that add up to 100 when subtracted make 50? And it's the absolute value, remember? So R can be 75 or 25, right? And S can be 75 or 25. So we don't know which one's which, but a good guess would probably be, since the bottle was supposed to be S, mostly S, you know, I think the best guess would be 75% S and 25% R. Okay. Okay, so some more real life applications of why we do observe different reactivities with stereoisomers. So there's a famous story, the thalidomide story. So how many stereocenters do you see in thalidomide? This is thalidomide right here. Just one, right? It's not that complicated of a molecule. But it was heralded as this big, great drug to rescue women that were experiencing severe morning sickness. Never got approved by the FDA for use in the U.S., so it was used, but it was used in other countries prior to discovering, you know, having long enough studies to see that it's not a good idea to give to pregnant women. So knowing that there's one stereocenter, that means there's 2 to the 1 possible stereoisomers. So there's just itself and it's an enantiomer. And so here's the problem. Our thalidomide is the one that you want to administer to the pregnant women. It's an antiemetic, which is a term that lets you know it's going to reduce nausea. It could provide a lot of relief. But S-thalidomide, it's an enantiomer, just that simple change of a dash to a wedge. is the opposite of what you'd want to give to pregnant women. It's a teratogen. Now, teratogens, anything that's classified as a teratogen is known to cause birth defects. So this specific one was kind of interesting because it targeted the arms and the legs, so it didn't grow as intended. So most of the time, the hands would be closer up here. In fact, there's a famous celebrity, Matt Fraser, who's bringing more awareness to this, who was a child born in that time period. And I put a picture of him here that I got from the show American Horror Story bio. But he's also made a musical called Thalidomide the Musical, which I haven't seen yet, but sounds interesting. But as you could see, it's not the entire, it doesn't affect the entire body growth. Everything else functions really well, but he had difficulty with the fact that he didn't have the full length arm. Just immediately his hands start almost right away, the joint to his hands. So it's kind of fascinating that something that looks so similar to its mirror image, very different reactivity in a chiral environment, right? So biologically speaking, it's really important to get enantiomerically pure drugs. So if there was a way to have isolated only the R and keep it R, because there's another issue that sometimes it can racemize in solution, which complicates it. But if there's a way to get the R and keep it in R and see after studies that it stays that way, then yeah, it actually probably would have been safe. But the problem is this is so devastating that it's really a high risk. So being able to separate enantiomers is really important. A lot of drugs are sold racemically because they've withstood the test of time as it not really mattering. One might cause a slightly bad side effect, nothing like this, whereas the other one has its intended purpose. And it's just so expensive to separate them because it's more difficult that oftentimes to keep them cheap, they're sold. So you're taking a dose of the enantiomer without needing it really. So manufacturers of thalidomide, they sold a racemic mixture. So equal parts bad and good, in other words. So why do we see such a big effect in biological environments? Well, enzymes and receptors are, you know it, proteins, which are made of amino acids. That's probably something you memorize like in every biology class you take. Building blocks of proteins are amino acids, right? But let's look at the structure of a typical amino acid, the generic structure, and it reveals a lot of the behavior. So here's the R group. That's the side chain. So that's the variable for the amino acid. The rest of it's the same. There's the carboxylic acid, and there's the amine, so amino acid. And then there's that carbon in the middle with some R group that could be one of many, 20 different R groups. Only one of them is achiral, and that's the one where R equals H. The rest of them, R is not one of the other groups attached to this carbon, therefore it is chiral. They're chiral. So all but one of them are chiral. So in other words, our body is filled with proteins and enzymes that are chiral. So it's no surprise it interacts uniquely with chiral molecules coming in, right? Okay, so to summarize the physical properties unit, achiral environments, beakers, air, etc. Pairs of enantiomers will have identical physical properties, except for rotation of plane polarized light. That's not a chiral environment. In chiral environments, like biological systems, right, living things, or synthetically chiral, like those columns I was telling you about, pairs of enantiomers will have different physical properties. And this is exactly what we need to separate them. We separate compounds in the lab using physical property differences. So when you sit back and think about it, what's easy to separate? Well, since diastereomers always have different physical properties, diastereomers are much easier to separate. Much more difficult, which is why many things are sold over the counter as racemic, is enantiomers. It takes much more money, effort, time to separate enantiomers. So it's only usually done if it's worth it. Thalidomide, it's obviously worth it, but it still has other problems that never made it worth pursuing that separation. So anyway, those are things that are very consequential to the pharmaceutical industry, medical field, and so chirality plays a big role in that, in biochemistry. Don't forget to do your homework. Use your models with you. Pull out Spartan if you need to. Draw dashes and wedges, and it will become second nature to start seeing those things.